Hello everyone, welcome back to Cambridge Guru. Today I'm going to discuss a very important derivation of a formula which is volume of a sphere. As we all know that volume of a sphere is given by 4 by 3 pi r cube. But from where this formula came? There are various derivations, various in the sense that we can derive this formula using various mathematical techniques. One kind of that technique is using the geometry, right, and using the approximation, just like we derive the area of a circle, right, by dividing the circle into a number of triangles, and when that triangle basically arcs or the different sectors, that sectors convert to triangles and that form a two-dimensional rectangle, and using the formula of rectangle we derive the area of circle. Similarly, we can apply various different types of geometrical approximation to find out the volume of a sphere. But today I'm going to discuss more easier method, easier in the sense that it is for higher classes, those students who know integration, right? And integration, in using integration also, there are single integral, which is basically a linear integral, and second we have some double integrals also, which is used to find out the surface areas, and there are triple integrals also to find out the volumes, right? But we are not using double or triple integral to find out the volume. We will use our simple integral, single integral, and we will use a very important, very beautiful concept in the application of integral, which is volume of rotation. So just to give some idea about what is volume of rotation, let us say you have been given a right angle triangle like this, and you are rotating this right angle triangle about this vertical or about this perpendicular length, rotating this 360 degrees about this line. So what you will generate is, you will get a cone, right? It will rotate like this 360 degrees, so you will get a three-dimensional figure, right? Similarly, if you have a rectangle and you are rotating about any length 360 degrees, same, right? So what you will get in this case is, you will get a cylinder, right? So using this concept, since we have been given a two-dimensional plane, two-dimensional figure, means we will use a single integral only, right? But we will try to improvise that integral using the volume of rotation concept. So when if we are able to rotate that two-dimensional figure, we will generate a three-dimensional figure, right? But in this case, since we have to derive the formula of sphere, volume of a sphere, so we need a circular figure, right? So we will take a simple circle and we will try to rotate that circle. And as you must have imagined now, that if we rotate a semicircle or a circle 360 degrees about any diameter, you will generate a sphere, right? So this concept we will use, right? So you have been given a semicircle, right, whose center is at O and its radius is, let us say, plus an r, or radius is just r, right? So this is minus r and this coordinate is plus r, or this length is plus r, right? And this is your origin O, right? So I hope that you know the equation of a circle which is having a center O. For that, if you do not know, we need that equation, because since we are using integration, so you must know the equation of a circle, which is x square plus y square is equal to r square. This is the equation of a circle with center at origin and radius as r. And now slight modification of this, I can write y square as r square minus x square within the square root, with not within the square root, and if you are using just y, then we will use the square root, right? Okay, so and this will be plus minus, but since we are using the upper part of a semicircle, so we will neglect the negative sign. Okay, so only plus sign, and we can remove also the plus sign. That means the upper portion of the semicircle, or the circle which is a semicircle, r square minus x square square root. So this equation we will use, right? Now, what this volume of rotation says, that you have you have to take a vertical strip. Its length will be y because it is in the y direction, right? And the width of this vertical strip is denoted by dx. Now the concept is that if you rotate this strip vertical strip 360 degrees about the x-axis, you will generate a disk, right? You will generate a disk because this has a slight, very minute thickness also, right? So let us take, you have a pen, right? Consider this as a strip, and if you rotate this 360 degrees about an axis, you will generate a circular disk with thickness as dx. Let me try to show this. My diagram won't be that accurate, but just to give you an idea that this will look like this circular figure. Okay, and this axis is passing through the center like this, and this width is dx. Okay, this width. So the vertical strip that you have been shown here is basically circular in shape like this. And if you rotate this, right, you will get a disk, right? Now another thing, that if I am talking about this height of this vertical strip as y, this is going to change. So this will be a variable, first thing. Second, that this will be the radius of this circular disk, right? Because if you are talking about the height of the disk from this axis, so it is denoted by y. So basically this will be the radius of that resultant disk. Okay, if this theory is clear to you, now we are in a position to find out the volume, and this is the concept which is called the volume of rotation, application of integration, volume of rotation, right? We are rotating a two-dimensional figure 360 degrees about an axis. This time the figure is a semicircle, and rotating this you will get a sphere, right? So if you have this disk, so I will say that the area of disk is denoted by capital A, right? And which is pi r square, right? Area will be pi r square, meaning pi y square. First thing is this, of this particular disk, and there will be infinite such disks, so we are going to integrate, right? Taking a small element and integrating between the limits will give you the area, but this time we are taking an area and integrating this within the limits, you will get the volume, right? You add all these infinite disks, you will get a volume. Okay, consider, let us say this is one disk, this is one disk, and this is one disk, so you will get, adding all these vertical strips, you will get the volume. Okay, fine. So volume of this small disk is denoted by dV, right? And if I multiply this area with its width dx, you will get the volume of this circular disk, right? So it is just surface area, area of cross section into the, if you multiply the area of cross section with the length, you will get the volume, right? This is in very lower classes, right? So volume will be area into dx. And what is this area? This is pi y square into dx. This is your volume of small disk. Now if I integrate this between the limits minus r to plus r, minus r to plus r, you will get the volume of sphere, right? So let us see if we are able to find out 4 by 3 pi r cube. So volume V is integral pi y square dx between minus r to plus r. Now I know the value of y, and these limits should be between minus r to plus r because y is a function of x. We are integrating this vertical strip, and we are moving this horizontally, so limits will be of x, right? So x, this will move from minus r to plus r. Okay, so put the value of y, which is r square minus x square, and if we square this under root will get vanished. So this will be given by taking pi outside the integral sign, y square will be just r square minus x square into dx from minus r to plus r, right? So this v is equal to pi. After integral, you will get r square into x minus x cube over 3, and limits are from minus r to plus r. Okay, so this is equal to pi, putting the upper limit, which will be r square into r minus r cube over 3. This is the upper limit value minus lower limit. So lower limit will be minus r. So it will be r square into minus r minus r cube by 3. Okay, there are a lot of minus signs, so just be careful. This is equal to pi integral, not integral, sorry. Inside the bracket we have r cube minus r cube by 3. This will be minus r cube minus r cube, and this will be minus minus plus, right? R cube by 3. Okay, so this is pi. If you open this bracket, you will get minus minus plus r cube, so you will get 2r cube minus twice of r cube by 3. So this is pi. Just a second, let me take this to other line. So this is pi into 6r cube minus 2r cube over 3, meaning volume of sphere, as we have expected, is coming out to be 4 by 3 pi r cube. Just see how beautiful this concept of integration is. Okay, rotating this, you will get a number of strips like this. Let me show you another strip. Okay, this is again dx, so this strip is moving from left to right like this. Okay, you will get infinite number of such strips, right? You will get area, and if you rotate all these strips, you will get the volume of rotation, which is in this case a sphere, right? I hope you have enjoyed the concept. Just wait for another concepts, right? Till then, bye bye, take care. I hope you have enjoyed this. Bye.